Awesome. Hello, everyone. Thanks for joining Dynamo's office hours today. Just to give a quick introduction, Dynamo is a high-throughput, low-latency framework for serving Gen AI and reasoning models at data center scale. And we constantly have the AI factory level in mind as we build, deploy, and optimize all our features. So today's session will focus on memory management, specifically the management of KV blocks at such a scale. I'm Akshita, a product manager for KVBM. Let me pull the slides. And we have three phenomenal engineers, experts, KV cache wizards, whatever you want to call them, across the Dynamo team. Would you like to introduce yourself?
Yeah, I'm John. I'm a deep learning algorithms engineer at NVIDIA, primarily focusing on Dynamo performance and KVBM.
Hi, I'm Ziqi. Yeah, I'm working on the KVBM team at NVIDIA.
Hey, I'm Ryan Olson, solution architect, and also kind of one of the lead architects on Dynamo.
Awesome, thank you. Perfect. We can go back to our slides. The Dynamo GitHub, as you know, Dynamo is an open source project. We have a public GitHub where we update our roadmap, all our code. So if you have any questions, please feel free to open issues, reach out there. We also have a Discord for our community members where you can ask all your questions. You can also email us directly on our community email, community@nvidia.com. And finally, because this session is about KVBM, while we go through a lot of things today, you can also look at our documentation pages and our GitHub, of course, to learn more about KVBM and Dynamo in general. You're also welcome to put questions in the live stream as usual, so you don't have to wait towards the end. You can put the questions in the live stream chat as we speak. Okay, perfect. Now with all the logistical stuff out of the way, let's get started. Most of you watching probably already know about KV caching, but let me very quickly level set about what prefix caching is and why it's important before we dive into all the fun, deep stuff. Next slide. Yep. So for enterprise use cases, so for example, we have long document Q&A or code gen use cases. A user might want to input a whole document or like say the whole Dynamo repository and then ask questions about it. So there's this context that will need to be used for all the subsequent questions. And often these questions are quite short. This is similarly the case with, like I said, with all these different system program chat history document use cases. Now, this information can just be stored. And storing this information avoids redundant calculations for earlier parts of the input, significantly speeding up the LLM's text generation process for long sequences. Now, without the KV cache, an LLM would have to compute all of these intermediate vectors for the entire sequence each time it generates a new token, leading to extremely slow inference times. Next slide, please. We just have a very quick visual here. The image on the left, it's pulled from an OpenAI developer community blog, just to show you an example of what prefix caching looks like, what a cache hit looks, what a cache miss looks like. I'll leave you a minute, just look at it. And the main thing, the main takeaway from the slide is, I think, not only what prefix caching looks like, but we wanted to focus on the cost benefits that come from cache hits versus cache misses. This is straight from OpenAI's GPT-5 pricing. As you can see, the price for a cache miss is $1.25 for 1 million tokens. And for a cache hit is just $0.125. So with about a 90% cache hit rate, like we see in agentic use cases, the cost of GPT-5 usage drops by about 81%. Next slide, please. Perfect. So now we know that caching is important. But why KVBM? So modern LLMs generate a lot of KV data that can't all fit in the fastest, the GPU memory. So spilling to lower larger storage is required to enable long context and larger workloads. Of course, this comes with performance and like a trade-off between the performance and the capacity. So using different tiers, balance it, like you somehow want to balance the speed, keeping hot KV blocks in GPU RAM or like the host memory while keeping the ones less used at the bottom. So that's pretty much it. KVBM is a runtime component that is designed to handle memory allocation, management, and remote sharing of KV blocks across all these storage and memory tiers. And before we move on, I kind of want to take just a little bit of a step back to level set. So like for Dynamo users, I'm actually curious if Zichi, if you could answer. Let's say Dynamo users have a lot of different use cases. Before we sing lores about all the amazing things we've done with KVBM and all the amazing performance stuff, what kind of use cases would not lead to a benefit in performance upon using KV caching?
Yeah, definitely. That's a great question to lay the ground. I think, KV cache offloading is not a one-size-fits-all for sure. So for certain cases, like when your workload have a decent cache hit rate, and also you do not have enough GPU cache space, then KVBM or KV cache offloading will definitely help significantly. But for some use cases, like you do not have a lot of cache hit, or you just have enough KV cache space in your GPU, or your KV transfer speed is not fast enough to do KV offloading, KV transfer, and last but not least, if you have like a huge KV cache pressure, maybe when you do KV offloading and KV onboarding, you do not have enough KV blocks to do that. So in those kind of scenarios, KVBM may not help.
Awesome. And what does huge KV cache pressure mean?
It just means like you have a huge amount of QPS, many requests, concurrent requests to the system that, you need a lot of KV blocks to accept those new requests.
Awesome. And I'm guessing that's probably the case, right? With retriever augmented generation use cases where sometimes instead of having the whole context, sometimes they decide to just summarize it and then feed it back. So then there won't be an exact prefix match, in which case, yeah, you probably wouldn't.
Yeah, exactly. So in that case, the prompt going to change a lot, so you won't have a lot of cache hit. But for multi-turn chat, for that kind of use case, you really have a lot of prompt prefix caching hit, so that we're going to benefit to use KVBM.
Awesome. Yeah. I think that was helpful just to like get a sense of where it's helpful versus where it's not. And then now we can go back to all the amazing performance numbers we have. And I know you were excited to share some of them as well. Next slide, please. Zichi, if you want to go ahead. Yeah,
sure. Then, let's take a look at how much KVBM can help on the performance before we get inside of KVBM. So here is a benchmark to showcase how much average TTFT, TTFT means time to first token, reduction that KVBM helps achieve. So it's basically the baseline is without using KVBM, right? And for KVBM in this setup, we set 100 gigabyte of CPU memory called KV cache offloading. In this case, we are not enabling disk or network storage. We are allocating 40 gig of GPU cache to make sure there's a decent cache hit on the CPU memory. Like what we said, if there's no cache hit on the CPU memory, there's no benefits to open up KVBM, right? So, and for the dataset, we are using a synthetic multi-turn chat dataset from Allen Benchmark, and this is an aggregated serving environment that we are using a Queen 332B, and this is using KVBM with VLLM integration. So we see across board, KVBM helps reduce TTFT significantly, based on different QPS. That means different workload to the system. We are achieving different amount of TTFT reduction.
Could you speak a little bit more about like a lot of these benefits depend on how much your GPU cache like size available is, how much the size of open GPU in the CPU is. So how do you set those numbers if you are allowed to set them in these experiments, but also in general? I'm sure we have more guidance coming along, but curious to know.
Yeah, I think it's more like your workload is not, for example, you set it, right? So for example, when you, especially for your GPU size, in our case, we know the data set is, right? We know the cardinality. The cardinality here means how many, for example, unique, KB blocks here, right? So because the data set we use, that tells us the cardinality in the trace, then we actually set the GPU KB cache size to be smaller in order to have cache it on the CPU side. But for realistic, like production workload, then it's actually based on your real workload, like what's the cardinality in your real workload trace. Then you can have some like rule of thumb to tune your CPU size or even your disk size to have enough KB cache space without wasting cost by deploying too much, like over provision too much.
Gotcha.
Next
Add
slide.
on, feel free to, yeah.
Yeah, next slide, please. Yeah, so we support KVBM in disaggregated serving setup as well. So disaggregated serving compared with aggregated serving is disaggregated serving is a serving architecture that we separate the prefill and decode phases onto different hardware resources, like onto different GPUs or even onto different node to do the trade-off and optimize for throughput and latency at the same time. So here is a similar benchmark we run on H100 with Queen 332B, but using 2 prefill workers, 2 decode workers, and TP2. And also, of course, the different QPS, we show significantly mean TTFT reduction. And specifically, KVBM is deployed in each prefill worker to do the KV offloading and the KV onboarding. And yeah, next slide, please. For this one, previous slide is about KVBM with VLM, and this with TRTM, and this slide is about KVBM with VLM. So we just want to highlight. So it's a similar setup. The major difference is we are running on H100 to test different hardware, and but the highlight we want to mention is for KVBM, we are not only support one engines, we support VLM, TRTM, and also we have plans for SGN as well. So yeah, and what we have here is, so you think about the data center setup, right? This kind of average TTFT reduction, it actually translates into a cost benefits, right? It means we can spend less on the prefill workers or devote more resources to the decode workers, so we can achieve cost saving or better overall performance.
Thank you. Perfect.
Any questions? If not, yeah, we can move to Ryan.
Just a quick reminder is feel free to all the listeners here, feel free to put your questions on chat. We don't have to wait towards the end. Yeah. Next slide, please. We just have a high-level architecture review of the Dynamo KV block manager and how it interfaces with different components of the LLM inference ecosystem, and how it kind of, we've isolated memory management from and the inference runtimes from KVBM itself. Ryan, do you want to share a little bit more about how we ensure this cross-inference runtime compatibility?
Yeah, with lots of talking, right? So because we have to rely, like our frameworks are great, right? All the inference frameworks, we want to work with every single inference framework. And to do that, we have to provide a common API that we can all agree on and define specific policies for that API. And so it is a work in progress with all of these framework developers to develop this kind of common interface. And once we have that, then we can generally, we as the KV block managers can work with each independent framework and tie into their systems, and then provide some extra benefits that we think will, provide the community good benefits regardless of which framework you choose to use. You'll get the same kind of general capabilities from the Dynamo KV block manager. So yeah, the interface is the most challenging part publicly. And then once you get past the interface, then you have all of the cool technology that we have going on under the covers. And so we can kind of break that down into kind of 3 groups. So we have kind of our core bits, and then we have these layout and block pools. So the layout pools and blocks, that little thing, you can kind of subdivide that into 2 regimes. We have 2 little boxes there. One of them is the layout, config, and type. But you can think of that more as the physical memory. So like how are the bytes in the various different storages? What do they look like? And then how do we manipulate those? The other box over there is the storage pools and block metadata. This is more like a logical representation of the blocks. Block ownership comes to mind, various different like and block ownership. Block ownership is probably the key one here, in the sense that you have to use the logical blocks to maintain ownership while blocks are being transferred or being used by the engines. And then under the hood, we let our transfer managers and some of our runtime compute kernels work on the physical parts of the blocks. And then down below that, we have our tie-ins. So CUDA is our #1 tie-in. So a lot of our transfers from between device and host will either use CUDA memcopy asyncs, or they'll use CUDA kernels if we have to fuse some sort of permutations with the transfers. And then anytime we go to any remote storage or onto say disk storage or anything else that NIXL supports. So NIXL has this fantastic set of pluggable backends. We leverage NIXL to provide a single interface to everything that's not CUDA. We go through the NIXL interface, and that way anyone who wants to come in and provide a NIXL plugin, then all of this KV block work will just naturally flow down through the NIXL integration layers between the block manager and the NIXL northbound interface.
So what I'm hearing you say is, like, for KVBM, they don't need to think about the memory layer for the most part, or how the transfers actually happen?
I mean, I think if you're a KV developer, you might want to look at the internals, but if you are just using the system, you kind of take what's inside KVBM for granted. And generally your primary hookups are your frameworks and then your backends. So you want to make sure that your backends, your data sources, are NIXL compatible or they're CUDA. And then you kind of let the black box of KVBM do the work. However, we do provide configuration options. We will provide more pluggability and the ability for you to basically implement interface classes to change the behavior of KVBM in the future. So all of these things, as we see the need arise, we will make them available.
Got it. Perfect. Next slide. Yeah, I think you alluded to this a little bit. John, do you want to just talk about our NIXL storage interface and in some way, like how we decouple memory management from KVBM?
Yeah, so as Ryan sort of alluded to, we use NIXL for block transfers for everything that's not between device and host. So for example, if you enable SSD offloading to transfer those blocks back, to eventually transfer those blocks back into GPU, we use NIXL. And within NIXL, there's really 2 key components. First of all, there's descriptors. So descriptors just represent a piece of memory. This could be a GPU memory, a CPU memory, a file, practically anything. The second part of this is how we actually perform transfers on these descriptors. And this is through what's called a backend. So some examples of backends that we use in KVBM are GPU direct storage for going between a GPU and SSD, and then also UCX for remote transfers. And these descriptors and backends come together into what's called a NIXL agent. Within this agent, we can specify what backends we'd like to use. We can then go and register our memory, meaning we go provide a pointer to NIXL representing our memory region, and then it returns what's called a descriptor. And with these descriptors, we can create transfer requests. So we can provide a list of source descriptors and destination descriptors and provide those to NIXL, and it handles, or it determines which backend to use to fulfill that transfer request. And this comes with a couple key benefits. Biggest one being abstraction. So we're able to use a very simple high-level API to interface with lower level complex transfer implementations, such as GPU direct storage or UCX. Second really nice thing about it is that there's no sort of backend specific logic that the user of NIXL needs to consider. So regardless of whether you want to do a transfer over like UCX or GPU direct storage, it uses an identical interface. So effectively, it just does all the hard work of figuring out how to get your data from your source to your destination.
Not sure. I think we had a question in the chat. How does KVBM decide which cached prefixes to evict under memory pressure? Is this LRU, LFU, recency, size, something custom?
Yeah, so we use a least recently used pattern. So what this means is, say we have a block and it hasn't been used in a while. It's going to gradually be moved up in the queue of blocks to evict. If we were to eventually get a cache hit on this block, it would then be moved to the back of the queue. And in this way, we effectively ensure that we keep around blocks that we're consistently reusing.
Awesome.
I will add that the future interface will allow you to provide your own custom. We'll have several more different examples of different strategies that are available, and there'll be a pretty clear place to implement your own strategies called the inactive block pool. And you can find that in the code, and that's where you provide your own custom interface or logic.
Like a follow-up to the caching prefixes, like how do we cache? What hashing do we use for prefix matching? Is like token level, block level?
Currently we use token level. So the way that it's done is we chunk up the sequence into chunks. We compute the hash of each chunk, and then we compute the hash of each chunk with its parent chunk. So that latter hash is called the sequence hash, and the local block hash is just a hash that's local. Right now that's a U64, so 8 bytes. In the future, we're moving to something that's called a positionally encoded sequence hash. So that will include the same information, but some of the bytes now encode the position of the blocks. So we can do some really interesting sparse positional rate extrusion.
And how does this cache look like? So for example, this hashed version, would it be different for different models? So if I have the same prompt or like the same prefix, would the end result be different for different models?
Really good question. The way that you get around that is you salt. So like the input sequence is the same across different models, but you do need to have a way to differentiate those bytes in that KV block came from model A or model B. Also, if they came from LoRa A or LoRa B, or if you just want to like isolate individual entities so that they don't have access to each other's KV blocks, you can choose to use a different salt on the hasher, and then that will naturally keep them separated. So yeah, we salt the hashes with you put into the salt whatever information that you need to uniqueify the data in those blocks that you need.
Okay, gotcha. And these KV blocks are not partially filled, right? It's either fully filled or like how does KVBM handle requests that might be shorter than like a block size itself?
We only work on block sizes.
Gotcha.
Yep.
Yeah, feel free to put questions in our chat. We can also move on to the next slide while we wait for questions. Yeah, we have a lot of exciting things planned. We have Dynamo releases every 2 weeks. We're fully open source. We're open source first now, so you can check out all our releases as and when they come on our GitHub. As mentioned, you can test out a lot of our KVBM stuff on going through the docs page or our GitHub. And but here's our roadmap, just to share it for the next few releases. We have planned performance improvement by integrating KVBM with KV-aware routing. We have the KV block manager that will be available as a separate pip wheel for modularity. So we ideally want it to be plug and play with inference engines and NIXL. And finally, we want to integrate with the G4 storage level and also offer object store support.
Someone might ask the question of what is G4? You want to tell us?
Yeah, thank you. Yeah, we have this internal jargon that we use all the time. Good question. Thank you. Yeah, it's the remote storage layer. So it could be, you could access it through file, you could access it through object, through block. Yeah, feel free to add anything that I might have missed there.
Yeah, so generally we say G1 means it's on device or on the GPU. G2 means it's in the host. G3 means it's somewhere kind of local to the node. So whether it's on like some sort of SSD, whether that's SSD is directly attached to the host, or if it's like it, kind of coupled over some sort of like mounted storage. But then G4 is not managed by KVBM. So that's kind of a big difference for G4. An example for G4 would be like an S3 object store. And so here, when we say this specific line is G4 integration, is to like an S3 type object store or other types of object stores, which has a slightly different set of rules and connotations that go along with it.
Gotcha. Thank you. Yeah, nice catch. I feel like we just have all of this internal jargon that we keep. Yeah, it's this whole cycle of just saying the same thing. So thanks for the catch. But yeah, like I said, we're open source first. You can find this roadmap online on our GitHub as well. Yeah, and you can learn more here. This is the link to our docs page. If you have any feedback or if you feel like there are things that we're not thinking about, please feel free to reach out through a GitHub issue. Thanks again for tuning in and being here with us. We really appreciate you all. And we'll hopefully see you soon in the next office hours. Thanks again.